Hey everyone, today we're going to put on our detective hats. We are going on a hunt for the odd one out, that one single signal hiding in a sea of noise. We're diving deep into a field called anomaly detection.
All right, let's kick things off with a little bit of a puzzle for you. So picture this. On one hand, you've got a hacker desperately trying to sneak into a secure network. And on the other, you have a tiny little sensor on a massive jet engine that's just starting to fail. Now, these two things seem completely unrelated, right? Well, it turns out they share something really fundamental. And the answer is, they're both anomalies. They are the odd ones out, the rare, totally unexpected events that stick out from the pattern. And believe me, learning how to spot them is one of the most critical challenges in the entire world of data today.
So, the big question is, how do we actually find them? Well, like any good detective, you can't just start snooping around randomly. You need a plan, you need a toolkit, and you absolutely have to understand the crime scene, which in our case is the data itself.
So, this is our mission, anomaly detection. That's the official name for this whole hunt. It's all about building systems that can automatically flag these outliers, these things that are just so different from the norm that they practically scream for our attention.
But here's the thing. Before we can even begin to find what's weird, we have to agree on what's not weird. So our first job, as data detectives, is to lay down the law. We have to establish a baseline and define the rules of what normal behavior actually looks like.
To figure out what's normal, our first stop is usually the mean, the average. This gives us the data's center of gravity. It's a single number that tries to represent the typical value. Think of it as our first, most basic clue about where the heart of our data really is.
But then we've got the median, the value that's literally right in the smack dab middle if you line everything up. And the median has a superpower. It is super robust. A few crazy, extreme values can't pull it off course, which makes it a much more trustworthy anchor when you suspect some outliers might already be lurking in your data. Okay, knowing the center is great, but it's not enough. We also have to know how spread out everything is, and that's where standard deviation comes in. It tells us, is the data all bunched up and consistent, or is it all over the place? A small number means things are predictable. A large one suggests a bit of chaos. But, and this is a big but, standard deviation itself can be thrown off by those extreme outliers, which can inflate it and actually help hide the very things we're trying to find. Now, if our data makes that classic, beautiful bell curve shape, we can use this really powerful rule of thumb called the empirical rule. It basically tells us that pretty much all of our data, like 99.7% of it, should be within 3 standard deviations of the average. So any data point that dares to step outside that range, well, that's our first prime suspect.
All right, so we've defined what normal looks like. We've got our basic tools in hand. Now let's head out on our first stakeout and see if we can catch some of the more obvious culprits. So, we've got 2 main tools in our starter kit here. First, the Z-Score. It's perfect for that nice, bell-shaped data we talked about. It just uses standard deviation as a yardstick. But what if your data is all skewed to one side? For that, we use the IQR method. And this one is clever. It totally ignores the extreme values at the ends and just focuses on that solid middle 50% of the data. It defines normal based only on that core group and then flags anything that's way too far away from it. Okay, so we've nabbed our first few outliers. It feels good. But, the criminal underworld of data is, well, it's complex. And in the modern world, the most dangerous anomalies don't stand out so easily. Our simple rules, they're about to fail us. And here's the problem. I want you to imagine not 1 or 2 measurements, but thousands of them happening all at once. An anomaly might look totally fine on every single one of those measurements if you look at them one by one. But it's the combination of all those values together that's just bizarre. These are the true masters of disguise, hiding in plain sight. So when those simple rules just don't cut it, it's time to call in the specialists. And in the world of data, our elite detectives are, you guessed it, machine learning algorithms. Let's meet 2 of the absolute best.
First up is a method called isolation forest, and honestly, this idea is just brilliant. Instead of trying to define what's normal, it flips the whole problem on its head. It tries to find what's easy to isolate. The logic is just so simple. Real anomalies are rare and different, so it should be way easier to separate them from the crowd than any single ordinary data point.
So, how does it actually work? Well, the algorithm just grabs a random chunk of data and starts making random cuts, or you could think of it as asking random questions, until a single data point is all by itself. And it does this over and over and over again. Now, the anomalies, because they're different, they get isolated in just a few cuts. The normal points, though, they're buried deep in the data crowd, so they take way more cuts to find. A short path to isolation means a high anomaly score. It's so elegant and ridiculously effective.
Okay, so our second elite hunter is the one-class support vector machine, or One-Class SVM. Now, if Isolation Forest is playing a game of 20 questions, this algorithm is the ultimate bouncer at the world's most exclusive club. Its entire job is to learn the exact shape of all the normal data points, and then draw the tightest possible boundary around them. If you're inside the rope, you're cool, you're normal. If you're left outside, sorry, you're an anomaly.
Now that boundary, that bouncer's rope, it has a technical name, a hyperplane. In just 2 dimensions, a hyperplane is easy. It's just a line. In 3 dimensions, it's a flat plane. But in the thousands of dimensions you find in modern data, it becomes this incredibly complex, multi-dimensional fence that perfectly wraps around all the normal data. And here's what's really cool. This entire super complex fence isn't defined by all the data points. Nope, it's held up only by the data points that are sitting right on the edge. These are called the support vectors. They're like the crucial posts holding the whole fence in place. The algorithm just focuses on these critical edge cases to define the entirety of what's normal. It's amazing.
So, why? Why do we build these complex digital detectives? Because this hunt for the odd one out, it isn't just some academic thought experiment. It's happening billions and billions of times every single day, protecting us in ways we don't even notice.
This is why it all matters. In cybersecurity, it's about finding that one single packet of data that could signal a massive network breach. In finance, it's catching the one fraudulent credit card transaction in a sea of millions of legit ones. It's stopping catastrophic failures in manufacturing by spotting a tiny sensor that's just starting to act up. And it's even helping doctors find early signs of disease in patient data. When you boil it all down, anomaly detection is kind of like the invisible immune system for a modern world. It's a silent guardian, a tireless detective on the job 24/7, just constantly searching for the things that don't belong, keeping our systems safe and everything running smoothly.
And that leaves us with one last big question. These systems are incredibly powerful, for sure, but remember, they're trained to find things that deviate from a normal that we define based on data from the past. So, what happens when something truly completely new comes along? Something we've never seen before and couldn't possibly anticipate? What's the one anomaly that they'll never see coming? Thanks for joining me.